Hello, my name's Nick Pears and I'm presenting Laplacian Iterative Closest Points, or LICP, for progressive registration of 3D human head meshes. My co-authors are Hang Dai, Will Smith and Hao Sun. This work addresses 3D to 3D shape registration. We want to morph the template shape on the right here to the target raw data on the left here, and the result is what we have in the center here. We're describing this morphing process, and it's guided by these features. 52 red points are face landmarks from the dlib landmarker. The blue landmarks are symmetry contour, and the cyan 55 points landmarks on each ear, all of which are extracted automatically. So this is the process we're trying to, or the framework rather, we're putting in a target scan here, and we have a template, and we're getting the output morph template here. So the target scan is fed off to the left and fed through the feature extractors, which extract features which we view as correspondence sets. So for example, if we extract this symmetry contour on the data, it can only match to the symmetry contour on the template. Looking at the center here, we have a variety of stages. We use 5. Early stages use few correspondence sets, such as the landmark based ones, low dimensional deformation models such as global affine, and as we progress through the stages, we use progressively more correspondence sets, and going from sparse to dense correspondence search, for example, and eventually we're using high dimensional deformation models that are Laplace-Beltrami regularized. So here's a morphing example. We have a raw scan of a baby from the headspace dataset on the right here. Here's the template, which is actually a symmetrized version of the face warehouse template. And our first stage is a global affine. Well, the first 2 stages, I've just put stage 2 here, is global affine deformation. Then we have something called sparse template adaptation, which is a bit like automatic mesh editing. It gets everything, the features in the right place. And then we move to dense morphing, and we can see that when we do dense morphing, some of the artifacts of template adaptation around the eyes and the domed cranium are resolved. And then we move to a refinement stage in stage 5 using shooting normals for correspondence, and we end up with something very close to the raw scan. So what we want to do is we want to evaluate this, and we decided to move to annotation transfer because of deficiencies in standard methods. These annotations are done manually, and they're labeled, so labeled with left lower eyelid and those kind of labels. What we can do is we can transfer these labels sketched on the raw 2D PNG images, and we can project them onto 3D. We can use that with the camera calibration matrices, for example, and then we do the morphing, and we hope that annotations tend to hit the same vertices on the templates irrespective of these really big shape differences between different subjects. And one way of testing that qualitatively is just flipping the annotations between the 2 subjects, which is what we do in the final column on the right here. So let's say we do this annotation transfer over 675 headspace subjects. Then what we're hoping to see is that the annotations hit the same places on the template, and we can color map that. So if these contours come out crisp and sharp, then we're probably getting good morphing, good correspondences, and if it's fuzzy and blurry, then perhaps we're not. What we want to do is come up with a couple of metrics to measure how well that's working, so numerical metrics. One is annotation transfer density, so that's just how it's kind of measuring how sharp that figure is that you saw in the last slide, and we try to compare this. Our algorithm is Laplacian ICP, and we tried it with kind of against our own framework, but with the shape regularization suggested by Amberg et al. In CVPR 2007, which is a per vertex affine constraint. And we can see that actually the per vertex affine constraint gets a slightly better performance in the mid stages, in stages 3 and 4, but by stage 5, our LICP has more or less caught up, so there's not really much difference at the end stage. And then we also tried this with another metric which measures how the labels mix when annotation transfer happens. So we want annotations of a certain label all to go to the same vertices and not mix together. We, for example, find mixing between the bottom of the top lip and the top of the bottom lip. So how well can we cope with that? And we compared the algorithms again, or the constraints rather, and there was very little difference between them. But the main advantage though of our algorithm over using the constraint from Amberg's work is much faster. We did some timing per stage, averaged over 118 headspace subjects, and remember the template's about 11.5k. This is just on a commodity consumer laptop, and we found that LICP, these are seconds here, does full morphing in 47 seconds, whereas when we use the per vertex affine constraint in our framework, it's over 20 minutes. So we find that in fact LICP is faster by a factor of around 26. So in conclusion, we have demonstrated that it is possible to use Laplacian mesh regularization to do fully dense shape morphing that is fast, fully automatic, and doesn't require training. Many thanks for your attention.